Welcome to this presentation, defect in solids. So here we are going to discuss about defects in solids. What is defects in solid? We will examine how the solid actually occurs in nature. Consider that a solid is made up of atoms or ions that are held together by covalent or ionic forces. It is axiomatic that atoms cannot be piled together and forced to form a periodic structure without mistakes being made. The second law of thermodynamics demands this. Such mistakes seriously affect the overall properties of the solid. Thus, defects in lattice are probably the most important aspect of the solid state, since it is impossible to avoid defects at the atomistic level. Two factors involved. One is the entropy effect, and the second one is the presence of impurities in any given solid. What we mean by this is that the chemical properties of the solid are not determined solely by its structure, but also by the nature of its chemical composition, and in particular by any defects that may be present. We will find that both the physical and chemical properties of solids are largely determined by the type and nature of defect present. It is axiomatic in inorganic chemistry that the perfect solid does not exist in nature, and its reactive properties are determined to a great extent by the defects present in its structure. We have already stated that some defects are related to the entropy of the solid, and the perfect solid would violate the second law of thermodynamics. And the second law states that zero entropy is only possible at absolute temperature. However, most solids exist at temperature for above absolute zero. Thus, most of the solids that we encounter are defect solids. The defects are usually point defects, which are atomistic defect in the lattice, such as vacancy, where the lattice structures lacks an atom ion. So crystalline solids are formed by regular repetition of a large number of unit cells in all directions. So as already we have mentioned that the perfect crystal constitutes of particle, atom, or ions are arranged in a precise geometric order. All the big crystals are found to have some discontinuity in the regularity of arrangement of unit cells. This discontinuity in arrangement of constituent is known as defects in solids. Types of defects. For a entropy effect are generally associated with a point defect in lattice. However, entropy can form stacking defect due either to slipped planes in the solid or to three-dimensional falls that occurred in the stacking process. How is this possible? You might consider that for any given solid, as the temperature rises, from absolute zero, most of the energy gain goes into vibrational energy. Recall what we said in the first part of formation of solid. Increasing the energy in a solid does not reorder the lattice and decrease the inherent point defects. For example, an atom of a gas has 3 degrees of freedom, the 3 spatial coordinate of the atom, and will therefore have an average total energy of 3 by 2 kV. For an atom in a solid, vibratory motion involves potential energy as well as restricted kinetic energy, and both modes will contribute a term 1 by 2 kT, resulting in an average total energy of 3 kV. Thus, it is the entropy of mixing that the force of creation of certain number of vacant lattice position above 0 degree Kelvin. Hence, vacancies are the natural result of thermodynamic equilibrium and not the result of accidental growth or sample propagation. And other factors also we can discuss. Here we have displayed types of defect. So point defect, so majorly it is classified into 3 types: point defect, line defect, and plane defect. And point defects are further classified into Schottky defect, Frenkel, and impurity defect. Line defects are classified into edge dislocation and screw dislocation and mixed dislocation. Then plane defects can be classified into grain boundary, stacking fault, twin boundary. Then we can discuss about point defect. So again, we start to discuss about a point defect. We have to find the defects in the solid. Stacking atoms or propagation units together a solid with a specific symmetry results. If we have done this properly, a perfect solid should result with no holes or defect in it. The second of thermodynamics demands that a certain number of point defects appear in the lattice. It is impossible to obtain a solid without some sort of defects. A perfect solid would have violated this law. The second law states that zero entropy is only possible at absolute zero temperature, since most solids exist at temperatures far from absolute zero. Those that we encounter are defect solids. It is natural to ask what the nature of the defect might be. Consider the surface of a solid. In the interior, we see a certain symmetry which depends upon the structure of the solid. As we approach the surface from the interior, the symmetry begins to change. At the very surface, the surface atoms see only half the symmetry that the interior atoms do. Reactions between solids take place at the surface. Thus, the surface of the solid represents a defect in itself, since it is not like the interior of the solid. In a 3-dimensional solid, we can postulate that there ought to be 3 types of defect, having either 1, 2, or 3 dimensions. Indeed, this exactly the case found for defect in solids. Specific name have been given to these 3 types of defects. Thus, 1-dimensional defect called a point defect, 2-dimensional defects called as line defect or line or edge defect, and 3-dimensional defect is called a plane or volume defect. Now we can discuss about point defect. Point defects are changes at atomistic level, while line and volume defects are changes in stacking of planes or groups of atoms in the structure. Note, the arrangement of the individual atoms are not affected. Only the method in which the structure units are assembled. Let us now examine each of these three types of defects in more detail, starting with the one-dimensional lattice defect and then with the multi-dimensional defects. We will find that specific types have been found to be associated with each type of dimensional defects which have specific effects upon the stability of the solid structure. Then a point defect is defined as the fault produced in the arrangement of a point. That is a constituent particle like atom or ion or molecule in a crystalline solid. Then the point defect can be classified into three types. One is a vacant defect, that is called a Schottky defect. Example, sodium chloride, potassium chloride, cesium chloride solids. And the interstitial defects is called as a Frenkel defect. Example, silver chloride and zinc sulfide solids. Then third one is impurity defect. Example, brass alloy and steel alloy. The point defect where we have discussed, we now need to determine how they affect the structure and chemical reactivity of the solids. We will begin by identifying various defects which can arise in solid, and later we'll show how they can manipulate it to obtain desirable properties not found in naturally formed solids. Since we have already defined solids as either homogeneous or heterogeneous, let us look first at the homogeneous types of solid. We will first restrict our discussion to solid which are stoichiometric, and later we'll examine solid which can be classified as non-stoichiometric or having an excess or one or another of one of the building blocks of the solid. These occur in semiconductors as well as types of electronically or optically active solids. Suppose you were given the problem of identifying defects in a homogeneous solid. Since all of the atoms in this type of solids are the same, the problem is somewhat simplified over that the heterogeneous. After some introspection, you could speculate that the homogeneous solid could have the following types of point defects. The point defects expected in homogeneous solid are vacancies, self-interstitial, substitutional impurities, and interstitial impurities. The two types of defects which involve the lattice itself, which will while the other involve impurity atoms. Indeed, there do not seem to any more than these four. And undoubtedly, no other have been observed. Note that we are limiting our defect family to point defects in the lattice and or ignoring line and volume defect of the lattice. These defects given are going to be discussed here. So vacancy or Schottky defect is defined as the defect produced due to the vacancy caused by absence of anion or cation, and cation in the crystal lattice is called a vacancy defect or Schottky defect. This defect was discovered by a German scientist, Schottky, in the year 1930. It is observed in ionic crystals, mostly in ionic crystal. Example, sodium chloride, potassium chloride, potassium bromide, etc. This vacancy defect or Schottky defect mainly occurs when both cation and anion leaves their sites and create the vacancies, two vacancies. One is anionic vacancy and cationic vacancy in the same solid. This type of crystal remains electrically neutral because both cation and anions were left their place. The presence of Starkey defect in a crystal decreases the density of the ions because uh, missing ions decreases or it loses the total mass, so that the density of the crystal or the solid will be less. Then interstitial defect or frontal defect. It is defined when cation or anion from ionic solid leaves its regular site and move to occupy a place between the lattice site called the interstitial position. The defect is called interstitial defect or frontal defect. This defect was found by Russian scientist Frankel in 1920s. This defect generally observed in case of relatively smaller cations, which can fit into the interstitial space and hence produces defect. Example, silver chloride and zinc sulfide. Here, chloride is somewhat bigger than silver ion, and the same way, sulfide ion is greater than zinc ion. Because of that, these cations can be placed in the interstitial position. The presence of Frankel defect in crystal does not change the density of the crystal. Then the next category is impurity defect. It is defined when a cation or a regular crystal is replaced with another cation. The defect is called the impurity defect. So here the new cation will be placed in the original cation, so that impurity. It is called as impurity defect. The different cations sometimes may occupy interstitial site also. The impurity cation is substituted in the place of regular cation. It is called a substitution impurity defect. For example, in brass, that kind of cations will be replaced in the original place. If the impurity cation is present in the interstitial position, it is called the interstitial impurity defect. That is, example for this kind of defect is steel. Then line defect. A line defect is defined as the irregularity in complete line or a row of lattice points of a constituent particle. Here, this line defect can be classified into three types. One is edge defect and screw dissociation and missed dislocation. Edge dislocation defect. It is due to the termination of plane of atoms. The particular plane of atoms will be terminated. That will be lost. So in the middle of a crystal is called as edge dislocation defect. In such a case, the adjacent plane are not straight, but instead bend around the edge of terminating plane, so that the crystal structure is perfectly ordered inside.